Yes, let's start.
Yeah. Okay, so
Should we start with the 5 other groups, or we start with the tutorial?
Maybe you can run through all the groups first, and then we do the tutorials.
Okay.
Yeah.
Then we would continue with group 6.
Hello, everyone.
Hello.
Hello. Can you hear me?
Yes.
I'm Cui Yanyu. I share my PPT. Okay. Can you see my PPT?
Yeah.
Yes.
Okay. Okay. Hello, Chaihua. Hello, Jagabu. Hello, everyone. We are 6 group. Our group members are Zhang Zhen, Yu Chuang, and me. My name is Cui Yanyu. Based on yesterday's discussion, our timber architecture design idea is 10 minutes prevailing. So you may ask, what does 10 minutes mean? Can people only stay in a prevailing for 10 minutes? Yes, I think 10 minutes is the time it takes for screening for the coronavirus 19 in a residential area. The screening or testing process includes take one's temperature, filling in epidemiological questionnaire. In Chinese, the word prevailing is a part of a stop. So 10 minutes prevailing means 10 minutes stop for testing. It is an interesting coincidence. As we all know, this year we all have to face a new situation, the outbreak of coronavirus 19. Over the past 6 months, our lives have changed dramatically since coronavirus struck. In China, more and more
Sorry?
I think we lost your audio. Can you still hear us?
Hello. Is other group members here? Oh.
Oh, I'm calling her. maybe we can go on the next group and
then we continue with you. Okay.
Yeah.
So then let's put Ben and Franz, I think, right now, and then if the connection problem is better, we can solve, then we can continue with group 6. Is that okay for you, Franz and Ben?
Yeah, that works for us.
Great.
Yeah, okay, so Franz and I are working together despite our very different time zones, but we're gonna make it work.
Adventurous.
Yes, yeah. So we decided to pursue the topic that I had mentioned earlier. So this is a project that I worked on previously. That image is from Woods Marsh, and these are from Arab. But basically, the specific project and part of the project that we've selected here is something that's a single instance of something that's probably like a relatively widely applicable problem that'll face timber multi-story buildings, especially as they become less regular. So this particular situation is one where you have a large cantilever span. Because it's this large cantilever, actually the initial design, the structural self-weight is about 60% of the total load. The live load is relatively low. It's like a hotel usage. So using timber has some potential to improve the demands in this. But the main problem that I see here is that whenever you want kind of non-orthogonal buildings, you'll often come up with instances where you have a cantilever or something where you need to project beams out and make them continuous in 2 directions. So with steel, that's relatively easy. You can have the beams in both directions in the same plane and weld them together. Same with concrete. You can have the beams in the same plane, and then you can just deviate the rebars so that they run next to each other or one on top of the other. But for timber beams, it's relatively hard to have them spliced together in the same plane. So a lot of design solutions tend to be something where you have one beam running in one direction, and then below that you've got a beam running in the other direction, which doubles your structural depth, and it also maybe can affect aesthetics. So we're trying to see if we can efficiently do this in timber, and if the potential of using robotic fabrication introduces some possibilities to lay the timber beams up in 2 directions, kind of stacked layer by layer. And so that's kind of the main design objective. And so the boundary conditions that we're working with here, it's half of a circle. The cantilever span is about 10 meters. The original design was something where you have 6 different tension columns that are like hung from above. And then there's some transfer beams and props that bring that back to the main structure from the roof level. But these support kind of circumferential beams shown in green there, and then you span cantilever beams out from that. And so because the concrete slab on top is in tension for cantilever, the concrete slab is just basically adding weight and not really helping too much in the primary structure. You're not allowed to take advantage of the composite action. So that's kind of an inefficiency that we're going to try to exploit a little bit. So this is kind of the boundary conditions. We're looking at it kind of being pinned, and then there's like a stiff beam along the perimeter. So when we run a topology optimization, it's also kind of apparent that the principal stresses, well, they do kind of, there does seem to be something where there's like a strong beam running along the columns, and then the slab kind of cantilevers out after that. It's potentially that like a purely radial and circumferential geometry isn't actually necessarily the most efficient structural solution. And so there's some potential here. We'll probably still run beams kind of in a radial direction as kind of primary beams, but they don't need to necessarily run straight out. There might be potential to do kind of a branching pattern. And it also kind of indicates that there's potential for like kind of some circumferential elements there, but definitely like the most efficient structure might not be just single massive members and kind of radial and circumferential. It might involve something where members kind of branch out a bit. And so this is kind of my interpretation of what kind of the center of the kind of main beam lines would be. So what we were thinking, we just drew it orthogonally here because it was easiest to do, but it's possible to do this at any angle really. But what we were thinking was to layer the timber members up. So on the top, not shown here, is the CLT slab. And then we stack two side members in several layers to kind of form a box. And that encloses the timber so that you only get charring from the outside. So potentially you could reach a higher fire rating, even though you're using lots of small members that are glued together. And then within these layers, the primary beams are shown as continuous in the bottom two layers. And then the secondary beams are basically penetrating through the primary beam's second layer here. So you could also have this secondary beam continue through to the other side. So that effectively makes kind of like a slightly less steep secondary beam. And by lapping them together like that, it's kind of a similar principle that's used in like cross-laminated timber, where you've got one direction of the layer much more effective in one direction than the other. Just extending that to the beams. And so that's basically where we've gotten to so far. Thanks.
Great. So this is a very specific situation that you chose, right? Which I think is very beneficial for the framing of your problem, right? And I guess given that you worked on the other project, it seems you also have a very clear understanding of what is really the problem to solve, right? So I'm super excited to see what comes out of it. Maybe one question that I would like to ask, which maybe you mentioned, but I didn't really understand. The building, as you showed it, was always conceived as a steel concrete structure, or was it supposed to be in timber and then was changed?
No. So the primary structure is concrete for this project. It's like a concrete. There's like a huge pool, which has needed concrete was like a good solution for that area.
Yeah.
This area, this lobe area, we use steel, unlike the normal concrete, because it was governed by self-weight, and so this was something where we were able to reduce the governing load for this part of the structure. So this was designed maybe like 8 years ago or so.
Yeah.
And I think only the first few big CLT buildings in Australia were around that time frame. So this is in Melbourne.
I see.
Yeah. So potentially it could have been considered to be in timber, but I mean, composite steel and RC slab is also like a very good efficient structure for something like this.
Yeah.
So it was like a reasonable design solution, but there's potential for timber also to be a competitive solution for this particular instance.
Yeah.
And that's what we kind of want to pursue in this project.
Yeah.
Yeah.
So that's I'm really fond of that. I think that's really adding a lot to the, let's say, more maybe explorative projects, right? With this being really hopefully going to be a very very technically and solution-oriented project, where hopefully by having the structure really be informed by those different flows as you showed it, will maybe not only see that this structure can be very efficient in Timber, but maybe can also offer some a certain kind of visual characteristic that maybe is more able to communicate what is actually going on within this structural situation, right?
Yeah.
So yeah, I think that's really cool approach. Very much looking forward to how it continues. I think coming up with your own kind of patterning of the beams is also great. I guess you would need to then also go a bit into how to adapt the tools that we provide, right? So I think, I think that's, let's say we didn't conceive of that pattern before, right? So it's not included yet in the programming tools. But if you feel up for that challenge, let's just do it. I think it's highly appreciated. I think the idea of having them overlap in a very controlled manner is probably very important if it's like a highly stressed region, right? And you really want to max out the capacity of this kind of beams.
Yeah, and one other kind of motivation for making the two-way grid kind of interlocks like this, so it's kind of somewhat homogeneous, is that also somewhat ties the CLT panels together above.
Yeah.
So we all know that like vibration is a big problem with CLT, and it's really something where there's like resonant vibration, which is all a frequency problem and damping problem, and then there's also something where it's just like lightweight, so each step is kind of bouncy.
Yeah.
That's really about mass, but it's not just purely mass. One of the big problems is that the CLT panels often aren't continuous. It's the modal mass. It's like each time you bounce, it only engages a very small part of the structure.
Yeah.
So by gluing these long members across the interface of different panels, you could potentially largely mitigate a lot of the vibration problems that like are the actual like governing design consideration for from like a structural aspect for CLT. So potentially also be able to get rid of having a topping for vibration problems.
Yeah, great.
Yeah.
Cool.
Can I add something?
Yeah, of course.
Sure.
Yeah, I really like this proposal, and what interested me the most is can you turn the slide to the yes, this one? And I think as you are an engineer, and I think it's quite very interesting to see that you are able to interpret the results we get from the topology optimization. And actually, I think we, as architects, I think as we are not that professional in the structure aspect, so that's why we provide the tool yesterday, and so you can easily get the pattern just from the mesh. But in my mind, as architect, what we want is also some creativity that we can input into our design, so we don't we won't be limited by the structural simulation software. So in my mind, I would encourage all of you, if you to maybe to reinterpret the pattern you get from the optimization yourself. And so in this way you can put your own thinking in the reinterpretation process, and actually this is also a process to make the design of the pattern, not just get the pattern from the optimization. But I understand that this process won't be a way that so automatically, but you need to draw your pattern yourself from the diagram you get from the structure simulation. But I think that's a better way that you put your design thinking in this process. Yeah.
And I wouldn't sell yourself short. Many architects have excellent structural intuition. Okay, so that's what we had for our group. So maybe we can go to the next group unless there's other questions.
Yep.
Group 6, are you ready now? Did you check if your connection is working better?
Yes.
Okay.
Yes, I'm ready. Yes.
Great.
Then we continue. Okay. Can you hear? Can you see the PPT? The second one.
No. Are you sharing?
Yes, I'm sharing. I have sharing.
I didn't see anything.
Sorry. Okay. Let me see. Okay.
Yeah.
Okay. Okay. Let's continue. I mean, wait means 10 minutes is the time it takes for the screening for the coroning 19 in the 19 in the residential area. The process includes take one's temperature, filling in epidemiological questionnaire, and so on. In Chinese, the word prevailing is a part of stop. So 10 minutes prevailing way means 10 minutes stop for testing. This is an interesting coincidence. As we all know, this year we all have to face a new situation, the outbreak of corona 19. Over the past 6 months, our lives have changed dramatically since virus struck. In China, more and more experts believe that we must be prepared to coexist with the virus for a long time. Therefore, we need to prepare space to prevent the virus. Focus on the residential area where we live. When prevention become daily, what kind of space is needed for screening and testing? It must be friendly and efficiency. Medical staff do not need to walk in the rain people do not need to fill in information on the ground, and the testing under the hot sun. In the changing climates, security and stability are most important. So the architecture must be security friendly and efficiency. Another important point is that we believe the materials need to be environmental friendly and reusable. So this problem are solved by, we believe that this problem are solved by robotic timber architecture with the following advantages. Robotic construction can reduce the risk of infection during construction. In extreme weather, it could provide temporary shelter for medical staff and residents to resist the scorching sun and the storm. Timber architecture is friendly to human perception and the environment. When the virus epidemic is over, they can be used as community public facilities and continue to be used. Then we choose a simple site for our study, Fengtai district in Beijing, where the epidemic is most severe in China currently. Next, we further selected the Yilan residential area in Fengtai district in Beijing, where is less than 1 kilometer away from the source of new infection, 新发地 area, new infection, 新发地 area. It is epidemic risk level is high. Virus carrier activity track cover this area. Then we selected 3 space, 3 places as candidates for the design site. They are in and around the residential area. Site area is one of our parameters. Final, we assumed parameters based on the site of public space. Let's take a look. Based on observations, if 60 people pass out every hour, and the screening process take 10 minutes, 10 people are tested every 10 minutes. Then if there are 5 groups of medical staff and equipments, 5 people in the waiting area in 10 minutes. In addition, we assume that no more than 5 patients will be in the treatment area. If the member exits, patients will be transferred to the nearest hospital. Another important point is that the distance between people should be keep at 1 meter throughout the process. In summary, according to the test process, we can draw 3 partitions of our pavilion: waiting area, testing area, and isolation area. According to the area of the site and the testing time, the number of people in each zone is limited, and the area of the zone can be calculated. This is the preliminary model from our team member Yuchang. We think each unit is hexagonal. The yellow units are the test area. The red units are isolate area. The blue units are waiting area. Red and yellow units are physical rooms with glass wall. The blue area is the waiting area. Only the roof, the height of the roof of the 3 functions may be different and need to be adjusted next. Above is our thinking and work. Thank you all. Thank you very much.
Okay. Can you go back to your proposed structure?
Sorry.
Can you show your screen again?
Well, I can't get your means. Can you say it again?
Well, it's okay. I think the motivation of your project is very honorable. What I what might be interesting to understand if the specific situation that you're describing, right, to kind of build this I guess pop-up shelters in the residential areas, it would be interesting to understand what are the specific characteristics that these structures need to deal with, right? And whether these are really rightfully addressed with let's say a building system as we are proposing it here, right? Or whether these specific characteristics are actually maybe a prime example of what you might want to rather address with a very standardized approach, right? So is what I would ask is, wouldn't it be maybe more accessible for this kind of problem, right? To say, okay, we need a testing facility that looks exactly like this. It might fit exactly into a module that is easily transportable, right? And then rather than building a building the structure with foundations and everything, rather keeping it temporary, right? Having the possibility to quickly remove it whenever you want, right? So I think maybe I don't know the answer to this, but it sounds like there's a specific connotation to your problem that actually caters way more towards a standardized approach, right? Which is not bad, right? But I guess for showcasing the flexibility, I'm really wondering how those testing stations would need to specifically address the situation on each site in terms of like, do they need to be different? Do they need to plug into specific situations and so forth?
Yes, thank you. Thank you. We will work continue for yes. Can we discuss discuss next time we should think about it.
Yeah, I mean, we can also just think about it right now. I mean, is something coming into your mind of how these testing stations need to differentiate from one place to the other? Is there a certain specificity to them, or would it maybe be better if they're just the same in each location?
It is better if they are different.
Okay. Yeah. Can you explain why?
I think different sites based on different residential area. The different area have a different population, the number of population. So only this reason, I believe it is different.
Okay. Yeah. But do they also need to look different spatially? Like, do they need to plug into like a specific corner, or like, I don't know, in a certain spot where maybe the boundary conditions are different from every situation?
Yes.
So I think these would be the questions that that would be most relevant to address. And then I guess it's great to go into depth about the current situation. Yeah, but I think as for this kind of project until Friday, maybe it's good if you focus more on the spatial problems at hand, right? And I guess you can outline the motivation for the project still very efficiently and very clearly in, let's say, 2 or 3 sentences, right? And then I guess the breadth of your work in terms of also what Hua and me can give you most feedback on, right, would be about the spatial configuration of these stations. But then maybe the next time we discuss would be really great to see this the 3-dimensional explorations on this. Okay.
Okay, thank you.
Thank you. All right, then we have 3 groups left. Group 3 would be Yuan, Shang, and Cheng. Group 8 with 3 members. Are you guys ready?
Hi.
Hello.
Yeah, I'm sharing my screen now.
Great.
Hi, I'm Xuexin, and we are Group 8. I'm with Lang and Yicheng. Oops, sorry. So our hypothesis or the concept is trying to create a system. We call it metaspace. With very simple grid and a simple setup, we can generate a flexible space. And this system also allows the users to define the space themselves, like the size of the space, the organization of the space, extra. It could be either a small pavilion, a villa, or a bigger scale, like a temporal exhibition place. Also could be considered as a metaspace app, so the users can adjust the parameters and even choose the patterns on the ceiling. It will automatically calculate the amount of the materials, the costs, and then as well as maybe the construction time. And after the user place order, so the robots will come to help to build on the construction. And regards to the prototype, this is just to show one possibilities. This is a 2 floors pavilion. Why we choose like 2 floors? One is we want to show the scenarios that this can be multiple layers, as well as to show by using this kind of methods, by placing a simple grid, we also could generate a dynamic, flexible, and interesting place. And this is like level 1 is more interior space with courtyard. And then the level 2 is like an open space with roof terrace. Also, we can insert the spiral staircase. And also for the F1 ceiling, maybe it's not very clear. For the F1 ceiling, we try to choose a more symmetrical shape. And for the F2, we choose a flow. We choose a flow frame, like an asymmetrical shape, to show we can have different conditions.
Okay. Yeah, you were muted for a second.
Yeah.
We heard you until different conditions.
At different conditions. And also we test the structure simulations with, this is with the tupus. It's quite heavily like on computing. And then also with the ISO curves, we think both could work. Or maybe the ISO curve is more integrated with the overall language, but I think both looks okay. Yeah, so that's it. I think we also have some questions. For example, for this ISO curve like generations, it is also like possible to optimize from the structure point of view. And also we would like to know how to calculate the quantity of the materials, as well as like, is there any way we can estimate the construction time by the robotic, like in an ideal situation?
Okay.
Yeah, that's it.
Great. Why you want to go first?
Okay. Yeah, maybe we can start with the questions like for these ISO curves, whether we can do another way of optimization on the structure, because this is just a random generate. It looks quite dense now. I think we might now need this kind of dense pattern.
Yeah. Okay, let's go first with the questions. And first, I think I'm glad to see the tools works for you. And for the optimization of the grid, I think first you can optimize the density of the curves from the input, some input parameter, right? And
Yeah.
if you want to use this kind of pattern to make some optimization, I think there are several ways, but I can only talk about the concept here, as we didn't prepare any like tutorials or tools for that. And first, maybe what you can do is you keep the pattern, you keep the density of the pattern, like the pattern is well designed, and then what you can optimize is the cross section of all the elements. And this way you can then use a plugin or a structural simulation tools to simulate the simulate all the elements as beams, and then you can get their force flow or stress in the beams, and then you can use the parameter, use the data from the structure simulation to optimize the height of the beams or the cross section, other parameter in the cross section. This is one way that you can do. Another way is that you can also try to use the similar thinking to optimize the density of the curves of the small segments. Like if you, I don't know if you are familiar. Sorry.
Yeah, I think roughly understand. So basically either optimize from the profile of the beam, or we can optimize the density.
Sorry, I don't quite get you.
Yeah, I think I get it. Yeah.
Yeah. Another way I mean is that you can actually use the similar way that we do the topology optimization. You can run a structural simulation, and then you can decide which element is more important and which is less important. And then you can delete the one that is not so important to the performance of the structure, and then run the simulation again. And this is like a loop, and you need to write for a lot of iterations, and then you can get optimized pattern.
Okay.
Yeah. But I think both of the method won't need other tools. You need other tools for both the simulation. So I don't think Topos can run this. You know the computation is highway when we do the topology optimization. So that's
very heavy.
Yeah. So you need another tools for structural simulation.
Maybe what you can do there is that there are some factors coming out of it. I'm not sure of it, but I think the stress factors are larger and bigger for the elements which attract more forces. So in that way, you can maybe derive back that the elements which have larger stresses, they will have a larger factor, and maybe that will give you an indication already with the current results.
Yeah. I think that's also a solution. You can have a try.
Okay, we'll try.
Great.
Thank you. Okay, so we'll keep on. Mm. Yeah. Yeah, understand. Yeah, can use the same algorithm to generate the
Yeah,
pattern.
the same language.
Mm. Yeah, the floor height is around 2.5 to 3 meters. Yeah. Mm, I see. Mm, disrupted. Mm. Okay, thank you.
And
Sound was off again. Yeah,
yes,
for the live stream. I'm so sorry that that happens.
Oh, Jakob, I had one comment or suggestion for the achieving like the really small isogrid on the previous group's presentation there. Like maybe what could be done is make a slab and then do like a subtractive manufacturing. So like a cutout to make the really fine isogrid and then use the robots to build up a coarser isogrid on top of that. That provides like the same visual effect that they're going for there while having like the deeper members be coarser, which are kind of easier to build.
So you mean it's more like
Suggestion.
the beam integrated with the slab?
Yeah, like have a deep CLT slab, but then like the bottom layer of the CLT, use like a CNC milling machine to cut out your isogrid pattern. Just like how they manufacture like the fairings on SpaceX rockets. But then make like pick out a coarser pattern of the isogrid and only like the coarser pattern attach additional members to make those like a little bit deeper.
Okay, thank you for suggestions.
Sure.
Okay. Group 9.
And I think they test me that they are not well prepared, and they just know they have to form a group.
Okay.
And maybe they will catch up later.
Okay.
Or,
Then Hanie, Sanas, and Fasani, do you want to present?
Yes, let me share my screen. Yeah. Well, we just tried some topology optimization, and for the first step, we used a simple surface with one column. In this case, we just didn't want any collision to be occurred while is assembling the beams on site, but because I wasn't sure that if one column can bear the loads of the whole loads of the slab and the beams, I tried to add some more columns for the first surface, and I added 2 more columns in different positions, but this time I didn't go through the analysis with this. Thought it would be more interesting if I use this surface as a module and develop it around a circle in order to have more directional slab with more columns. It's I think it's more it's more feasible in terms of structure because it comes and also it's the shape of it, it's more dynamic, and also people can use the central space in their quality time maybe. Finally I obtained this shape. And in order to develop my work, I just wanted to use the curves that I obtained from the topology optimization as some guides for the, let me, yeah. Sorry. Let me just show it from the pictures here. I used curves as some directions for the final timber beams. So I offset the curves and use these offsets for the final beams. But I have some problems here. I have a question. As you might see here, there are some gaps between these beams, and I'm not sure if it's logical in terms of structure stability, I mean structural matters. If we, when we want to assemble the final structure, if it's logical to have some separate individual sections, or we have to design a set of beams that are connected together and joined together all around the surface.
Okay. So about the beams, I think that's exactly what we're gonna focus in the tutorials following right now. After that,
okay.
For the different spatial configurations, I'm really fond of your of what we can see right now on the screen, right?
Mm-hmm.
I think that's really, let's say, a nice combination of simplicity at the same time, showcasing like a couple of situations that probably as well are, let's say, multi-directional, right? You have the radial situation, right, where you could say, okay, around the ring, you would just have like I guess just a ring of beams, right? But then really the question for dealing with this would be to how do you integrate these cantilevers, right? And how do you integrate those into the overall system? So I think if you're okay with it, just go forward with this. And then after today, I think you're gonna also have a bit more information about how we can explore the beam tectonics, right? Maybe for simulating your structure, it would be good if you could put a lower resolution, or a higher resolution to your simulation, right? Which obviously is going to be restricted by your computation that you have available, right? But maybe as a as a simplification, you can also just simulate one of those kind of spikes, right? And then derive your beam pattern from that, right? And then you could just radially arrange it. I guess that would be definitely
you mean that
possible.
I first obtain the curves for just one module and then I develop it myself?
Yeah, of course you would need to be very careful that the beams here are continuous then in the end, right? But I think for the simulation, that would be definitely possible, right? Maybe you would want to put an additional load here, right, to indicate that it's continuous, or actually, I'm not sure if that's possible, but kind of constraining it in certain directions in the simulation. But yeah, maybe one of the engineers can give a bit more feedback on that later.
Okay.
But for now, I think this kind of topology would be quite interesting. What do you think, Hua?
Can you hear me?
Yes, Anas?
Let me share my screen. Okay. Because the curves and freeforms are the more optimized forms, I choose them. And to make my freeform, at the first step, I consider the real line.
We don't have your, I think.
What?
We don't, I can't see your screen. Yes, it's here right now.
Yeah, I see it.
Okay, I can start the line with 120 degree between them due to they are at the most stable position to each other. And I try to choose random points on these lines. And after that, I tried to make my model with metaball components, but still I wanted to have more control on my form. So I tried another way. I made circle with the considering those random points as a plane for this circle, and again choose random points on my circle. And so with interpolating these points, we could have our free forms. And I could make various forms with direct control on them by changing my number sliders. And I try to have it, and I try to consider at 2 level to make it attractive, and but at the same time I try to have a minimum overlapping of them to optimization usage of material. So I try to make these shapes. And I try to make their ISO curves with Topos plugin. And I want to add it, we could optimize these forms based on minimum stress and better ISO curves by changing our number sliders if we defined it to Galapagos. And thank you.
Thank you.
Can you hear me?
Yeah.
I wanted to show another pattern. We are working on it, and just a quick brief of it. Okay, we as the third pattern, we choose some kind of Iranian pattern, which can considered as an archetype. We choose it because it is ancient and also they follow the specific geometry, and we can develop it. In this case, we have two different patterns. The stars, which you see in this pattern, are some slabs, can considered as slabs with one column, and the other patterns are empty, and it help to have a good shadows when sun is rising, or they can also produce some great patterns on the ground. Okay, this is, let me show you. These are my patterns, and we can arrange it in different ways to have some different shadows. As you see here, and
I think we still see the screenshot.
Oh, let me.
The black and white patterns.
Let me share screen again. Is it okay right now?
Yeah.
Okay. As you see picture in this model, we can produce a lot of patterns here with different kind of shapes, as you see, and displays are empty places, and here we have another kind of places, and we can repeat this kind of pattern to have some great shelters, maybe some shading device, maybe. And this is just an idea which we had, which we worked on it last night with our friends, and I just prefer to show you and to know your ideas about them. Thank you.
Okay. Very interesting studies. Also, always quite exciting to see the approaches from all over the world to different patterning and this kind of explorations. I think what will be most important for you guys as a group is to start working together and to develop, I guess, one main concept forwards, right? As you just formed the group a couple of hours ago, or let's say half a day ago, I think it's totally fine for now, but maybe starting from tomorrow you should maybe consider to have like one presentation that shows your project as a group, right? Okay, with that, if Hua doesn't have any other comments, then could go on with the tutorial for the beam tectonics.
I need to, so yeah, let's move on to the next part. Okay.
Yep. Thanks, Sanas, Mahanie, and Aksani.
Okay. I will share. Can you see my presentation?
Yes.
Great. So today the tutorials will be the beam tectonics. Will show the example of the beam generation program that could generate a building system with a small number elements. Build the beams that we generated yesterday. Get going. Oh. Okay. So today we move to the beam layout part, and actually, yeah, I think you have already seen this slide several times, and from the network yesterday, I think there's a lot of ways to make the network a reasonable tectonic system to be fabricated. This is just several options that we want to show you. And for the tutorials, we only choose the first case. So the tutorial just want to show you how to generate the beams tectonics from the network we generated yesterday, and how to make it a very appropriate structure that could be fabricated by the robot. But I want to repeat again that the tools we provide today, I want to introduce today is just the same, the first option, and you are encouraged to develop your own patterns or your own tectonic system if you think you're capable of that, and also we don't set much limitation on that. So if you go to the Google Drive folder, you can find a shared folder for day 4. It's day 4, right? And there's a GH files there called beam generation, and you can download it and open it. We can take a look at the files together. It's just a GH file and without the lens in the Rhino model, and they are all internalized here, and I just pick them so that you can see all the lines here. So while you are downloading or you are trying to open the files, I will give a brief introduction of the program, and so you can see what we're gonna do today. And what we want to do is to try to use the network we generated yesterday and transform it to a beam system that could be fabricated while beam tectonic system that could be used for the real construction. And there is several steps from the initial input lines to the final structure. And I think we can separate the process into 3 parts. The first part is try to optimize the input curves, and so that it's fun. So we can use the optimized curve to generate our beams tectonic. And the second part, so the second part is just to use the curve we get from the first part and generate the beam layout based on the curves. But in this case, you can see that what we get is 2 layers of you can see the white line and the black line. There are 2 layers of beam layout, and they overlapped with each other, and that's what we get from the second part. And for the third part, we just use we take the results from the topos optimization yesterday. We get the location of all the points in the optimization and the density values from the optimization, and try to optimize the height of the beams and generate the beams as the brief. You can preview, yeah. So you can see the height of the beam is changing well at the different locations, just according to the structural result. If you're ready, let's get started. from the first part. So uh, to generate the beams, we have the input curves, but the input curves may not well fit the element size that we want to use. And if you still remember the platform we are using, we just try to use a standard element and just grip the elements when through the elements when it is through the glue station and put it in position and nail them. So what we want to do is to have all the curves that could be well fit by the element, the standard element we want to use. But at the same time, we don't want to have any collisions between all the elements, and we want to have two layers of elements, and they could overlap, have a certain area of overlap, so we can put nail in the overlapped area and also put glues in the on the interface, so we can connect them properly. So what we are using to optimize the input curve to the curves that we can use to generate the beams is the program in the first part. I think we call it agent-based modeling system, and when we say that, that means that we in this program we view every point in the every intersection point in the input curve as the agent, and what we want to do is try to move the point location and make the length of the segment or or we can say the distance between all the agents of the point be kept in a certain distance or certain or the length of the segment be kept in a certain value. So we may, to optimize that, we may have several different scenarios to consider. First, we may have some segment that is too small to fit in element. So in this case, when we try to fit a block like this, and when we want to put another block, can I draw here? Yeah. On the next segment, there will be collision here, right? So I will went through all the situations first, and then try to explain what we can do to solve all the problems. And then in another part, maybe we have a longer segment here, and when we try to fit element in, and maybe we have another one here, and we fit an element here, but the distance in between is too large, so it's when we put another element on the next layer up next layer upon this layer. So the element won't have any area that could overlap. So we have nowhere to put the nails and the glues. So that will also be a problem. And another situation is that we have a very long curves and the distance between the 2 points. And in this way, what actually we can put multi elements in this one curve. So this is the 3 situation that we need to solve. And besides, in addition to these 3 different lengths of segment situation, we will have another situation is that at every intersections, I will like here we have 3 lines intersect at one point, and when we want to put elements here, here, and here, most commonly we will get some get some collision here. So this is a false situation we need to solve. So let's explain what we can do to solve all these problems. So when we call the method, we are using agent-based modeling. So for all the agents, we can give them several behaviors to interact with each other. So like they could organize themselves with other behavior to form to solve some problems that we want. So the first behavior we want to give to the agents is try to deal with the first very short segment. It's a repulsion. That means that when we have very short ones, we will define tolerance when when the distance is smaller than a certain number. What we can do is we give a vector to each agent or each point at the end of this curve. So they will try to push each other away. So in this way we will have a longer curves. So this is for the first situation. And for the second one, we'll have a longer curve. And also we want to do is also to keep the distance between these 2 agents in a certain number. So what we can do is try to give them a vector to move towards each other. So we call it attraction. So in this way, we are able to manage to keep the length of this kind of segment in a certain distance that we are satisfied. And for this next, when the length of the segment or the distance between the agents exceed some certain tolerance, or some threshold we set. We want to put like a multi blocks, multi elements on this curve. So what we can do here is try to subdivide the curve here in the middle, and then we will get not in the middle, just in a certain length that could fit in a new one. So that if we have a very long one, maybe we need to subdivide it into 3 segments. So just in this case, we can divide this curve into 2, and in this way, we will add a new agent here into our system. So we will have one more agent and 2 connections between the agents. So in the next iteration, this one will also act as an agent. This one will also have the behavior that we defined before. It will try to if the distance between this point with other points reach a threshold, it will try to push or pull the point together or away. So in this case, we will need to add new agents into our system. Okay. So we have already talked about the 3 situations here in the length of the segment or in the distance between the points. In the next one we have talked about is to avoid all the collision points. To avoid all the collision points that occurred at the intersections. So if you see the blue rectangles, that's where we want to put the elements first, but we will have the yellow points at the collision points. So in this case, what we can do is try to push all the points that's connected to this intersection point away from each other. So in this case, we will get block also move away from this intersection point. So we'll maybe, if we run several times or we optimize very well, we will get the rectangle in the right. So you can see there will be no collision. So that's the principle. That's all the behavior we want to use to optimize our input curves, to optimize them into a very appropriate curve that we could use to generate our beam layout. So in this case, when I talked about the block before, I mean we can put both elements at both sides. The gray block here, they all represent a timber block, a timber element. And so we have 2 rows of timber elements, and we will have one in this direction, so they can connect the 2 rows together. But what they connect is it's the elements on the upper or lower layers. So you can see when we put elements on the up layers, this block in this direction will try to connect these 2 rows together, and we will have intersection part here, and we can put our glues and nail them together. So this is pretty much the way we do to optimize the input curves. So let's see how it works in the program. And so in the input part, you will have two options. The first one is it's all the beams here. The second part, second one is only the three segment here. So if you maybe you can take a look at the simple one, so we can get a better understanding how it works. So let's change this one here to 2. So we will make the input as the 3 curves here. So for the program, we will let's look at all the inputs so we can understand what we need to do the optimization. First, the innate lines, which is is the lens that we get from the it's the lens that we get from the network generation. So we just take this as input, and this is the process that try to intersect all the segments. That means if you have some grid draw like this part will try to intersect all the curves and get small segments for you. So the input is 3 curve, the output will be small segment like this. So what the program need for the input is always the small segment that have no overlap or have no overlap with each other, and they will all be split at the intersection point. This is just what this part to you can read yourself. Okay? And the second input is the anchor point. What the anchor point means is if you still remember from last tutorials, we have column, the point of columns that we have them fixed when we do the relaxation dynamic relaxation. So also in this part, when we make the optimization of the beams, we also want to make sure that the agent or the point at the column, at the top of the column, would not move anywhere. It will just we will just set them as anchor points. So this is also from the input. And the iteration count is how many iterations we want to run this optimization. I don't have to explain that, right? So there are several, how many? It's 3 parameters, which is directly related to the size of the element we want to use. But there's something I want to make it clear, so you won't misunderstand maybe this way. So when you see a beam here, what we mean is always a beam is always maybe the line will represent a beam, and also a block like this will also represent a beam. That's a beam means in this program. But when you see beam, I really need to. Yes. So in this part, we only need to input the yeah. So the right block you see here is what we call a beam here. So what we input as beam length and the beam width, it's always this is the length, this direction is the longer direction, and in this direction we call it a width. But when you see element thickness or element width, we mean the gray element here. That is a real timber element we use to fabricate the structure. So when we say beam, we mean abstract rectangle that will bound the beams here, bound the element here. But when we say elements, it's the real element we use to fabricate. But the element thickness and the element width is used for the next and the third part. So I just post the parameter here. So, but don't make this confuse you that we what we need for the first part is only the beam, only the length and width of the beam. Okay. Yes, and the beam length is always equal to the element length. Yes, the length here, the element and the beam, they have the same length, but they have different widths. And only the height, the elements have a thickness. Okay. And for the next part, we will have two strengths as to input as strengths. One is attraction, another is repulsion. And that these two parameters just referring to these two behavior, how large the repulsion we want, and how large the attraction force we want. And but you don't see any strength for the subdivision, because when it reaches threshold, it will just subdivide it. So we don't need parameter inputs for this behavior. And we also don't have one for the collision, because I set the force, the strength for collision as 1. So the default strength for collision is always 1. So that's our most important destination, as we want to avoid all the collision. That's the most important behavior. So, and all the strength is of attraction and repulsion is always smaller than 1. And so we just need to impose these two, and they are proportion. You can view them as the proportion of the strength of collision avoided. And yeah, that was the attraction strength and repulsion strength in here. And for the last part is the Boolean button we use at the we call it the I collision. That just means that if we want to use if we want to avoid the collision, you will see why I set it here. Because actually you will have more problem when you are trying to use this program, because it's sometimes it doesn't run that well. But when we don't try to avoid the collisions, it could get the pattern that looks quite well, but it's not feasible for fabrication. If we turn this as true to avoid all the collisions, we will have some problem somewhere, and we need a lot of pay a lot of attentions on the impulse curves to avoid all the problem in the collision. You will see later. So let's see. So in this term, we import the 3 segments here, and we set it as a fixed point, and we run it through this program, and what we get here. Actually, you can see some of the curve have already deviate from the original curve, and the length of the curve have already changed. Maybe if we bake it, try to check. Yes, we have 2 segments at the longer ones. That because this one have already been divided as 2 segments, so we can fit the. And so I hope you can get understanding of how this program works. So I turn to here any. Yeah, in this case, maybe there's no collision at all at the first place. So it doesn't matter whether we try to avoid the collision. And let me see how we proceed. Maybe we talk about this part and then we go back to the whole structure. And the second part is try to take the output from the first program and then try to generate the 2 layers of this kind of beam layout based on the curves we get. And let's get a quick look of. And it takes output from this program, the line output from the previous program as input. And it's share the same parameters with the first program. It also uses the beam length, beam width to generate the beams, and it also have element width. That's I have already explained the width of the gray block and this yellow block. And the beam thickness is try to make a distance between the 2 layers that we generate. And what is the output is this is the first layer of beam layout. You can see we have one here, and we actually have 2 here. And if the distance between these 2 elements is enough to fit in element in this direction, it will just generate 1 element here. And for the next layer, it will just connect the the first layer with this same element, and you can see there's no collisions between at the intersections, and this kind of beams will well connected all the elements in different layers, and we have properly intersect area that we could put the glue and the nails. So this looks fun, and yes, as we get just the two patterns onto plan. So this is not this is still not the final beams that we use. So let's see. So in this part, there's it still use the agent-based modeling, but what it's the most important thing for this part is try to draw the elements. So there's not much to explain in this program. So if you get have already have the curves from the previous optimization process, you can just draw a block, right? And you can draw the block here, and then this is just some geometric drawings. I won't much attention on this part. So actually, if you have the curves there, you can program your own program here to generate different beam layout here. So maybe you can try different layouts that we provide here, or you can invent your own layouts. They're all free in this part. But if you don't want to do that, if you want to use the one that we provide, is all up to you. And then let's try to see what we can get from the very complex pattern that we get from the optimization yesterday. Let's change this to 1. So we get this pattern as the input, and have like 5 columns as a fixed point at anchor point, optimize the curves. And you can see it will work in a much slower way. So let's take a look of the result. Now maybe let's keep this true at first place. Now, yeah, you can see let's select some area, maybe we keep it here. Yeah, you can see if we want to generate beams here, this segment is not longer enough, so it will be pushed away, and this is also not longer enough, so it also will be pushed away. So after all the movements of all the iterations we optimized, so the location of the beams may change. We may deviate from the one that we defined as the first place, but I think they won't move too much. And you can see we probably avoid some of the collision at the joint, and but yeah, there's still some problems that need to be optimized. But you know, in the computational optimization process. Sometimes it just doesn't work out for all the situations. But for most parts, I think it's quite desirable. Yeah. But if you actually this pattern as input is already being optimized manually by me, and so you can see this pattern. There won't be too much problem in these patterns. But if you draw it yourself, you have too many small segments or very long segments, and the program may generate several situations that we are not satisfied. We don't want that. Maybe like let's take maybe just take this as input and see what we can get. And then you may see where the problem is. And we take these three curves as input. We'll compute and what we take this as intersection point as anchor point. Yep. So I think we have some problem here. Maybe oh sorry. I think I called some curves manually here and I forgot to. One, two, three. Okay. That's So if you can see this is totally not what we want. And yeah, and actually in the optimize, there's some very weird thing happens. I did this. Yeah, maybe we try some different patterns. Yeah, this one works pretty cool. And I think it also works on this one. And I don't know what happened in the next example. But if you have more maybe more segments. Yeah, it works quite good in this case, but I'm sure you will have your own problem when you are using this program, but hope it works for you. But if it doesn't work or in some certain situations, I would recommend you turn this angle to false, so it won't do the check for the collisions, but it will generate a similar patterns looks like this. And we will just need to keep the collision here. So the Python will just for a preview of the final structure. It also won't make too much sense as we don't optimize it to a certain state. But in this case, we will get a pattern like that looks very similar to the ones that would be optimized if you can take this. And so now we have the patterns and we have the layout of the beams. What we want to do is to generate the beams. To generate the beams of the final structure. So to do that, we need to set some anchor points. So yeah. I see where problem. So in the third part, what we want to, as I already said, is that we take the outputs from the topos optimization. We take the location and the density of the point as the input for the optimization, so that we can optimize the height of the beams according to the structural simulation result. So just in this case, as this was plotted manually by hand just now, so we don't have this to import. So you can see the height of the beams doesn't change too much. So we went back to our example files at the first place. It needs some time to, and make sure select the first case. Now we get the pattern here and also the final beams here. And you can see the beam layout and the height. And yeah, let's keep going. So take the pattern here and the structure property here. What we do is to first we get the data for the structural properties, and then we try to change the data into the height of the beams. So what we do is try to remap the data into different numbers of height. So if we have a curve here, and the curve, the structure here is the density here is very large. So in this case, maybe we need to remap the height of the beam here to a larger value of the layer of the beams. So here we have two numbers. Is one is at the lower threshold of the height of the beam. So we set it to 1, but you can change the maximum of layers as you want. And here we set it to 5. And so the density of the structural property will be remapped to some integer from 1 to 5, just 1, 2, 3, 4, 5. That's the only 5 choice we have for the height of the beams. So when we say 1 layers, we mean this two layers, that two different layers. We call it 1 layer in the optimization process. Okay, so this 2 layer forms one layers in this process, but there are 2 different layers in the beam generation part. So so this part is just let's see, we have the lines. First, we have all the center curves for the beams, and what we do is try to get the center point of this curve. And we try to find the closest point in the point cloud that generate nothing here. Aha, I put the wrong one again. I will update the files later, but let's keep the tutorials. I just check the results. It seems fun, so I just see. Yes, and what we want to do is try to find the closest point in the structural simulation, and also from that we get the property that is gets the property of the location, gets the density property of the location. So we remap that density here to the integers, and we select the same index of the density and the location. So we will set the density value as and transform the density value to the height of the beams, and try to set it to the beams here. So for the elements, each element will try to find the closest point in this set. So you will know which element, this element is closest to which curve, so that it will also get the same value from the curve of the height of the beam. So this curve, if we set this curve, the height of this curve as 2, so the closest point here, the closest elements here, will also get the value 2 for the height. And then we will try to just move them into different layers and extrude the bit. That's what we do here in this part. And I think if you can read it yourself. But we have another C# program in between. And that's why now you can see there's two different or several different layers of the beam, even though we have the wrong input of the structure property. That's what we do in this one, is try to keep all the elements, keep the change of the height in a very slow way. And I in this program, I set the height at the anchor points to maximum. So if you have a column, you will have a 5 layer at the column, and then it will try to decrease the height according to the structural property, just in a very keep it continuously and not very so there won't be any change that very steep. And I think I will update this part so you can get a better understanding of what we do here. Maybe I will make the modification now while I will answer your question, and before yeah, maybe I can answer your question now, and then after that I will update the files and you can have a look at of this have a look at of this yourself. Is that okay? Yes. Again. I think we have several questions in the chat window. First, did you define the distance between overload points or the basic in the C# code as in import the distance with an offset? So I don't get this question. Actually, do you mean the threshold that we define here, where to push them and where to pull them together and when to subdivide them? We have one input as a collision distance. This input is the one that control all the distancing of all the points. So this collision distance need to be larger than the beam length. Always be larger than the beam length, so we don't have collisions. So if it's smaller than the collision distance, it will just try to push each other away. And if it's larger, it will try to pull them back. And yeah, it's based on a module of its option. I think the collision distance, the distance between the points, need to be based on your on the element, the size of elements you want to use, and you set this collision distance. Make sure that the different layers have a certain a certain contact area. What about beam length? Beam length equal element length. Yes, beam length is the same with the element length. Sorry, I don't understand the location component. It can be an internalized mesh from previous content. Okay, the location, actually the location is, maybe I can open files from yesterday. If you have this battery, and you will have a output as location, and then the second is as density. And what we do is take this to as input for our height optimization. Okay. Yeah. It's actually two parameters here: location and density. How can we change the pattern of the connections? So what do you mean by the pattern of the connection? Yeah. Yeah. Are you here? I see the question you sent to me.
Yeah, it's from Sadra, from the live chat.
I don't quite understand what's the pattern of the connection.
Maybe the patterns that we showed in the previous slide. Yeah, what you mentioned in the presentation is writing.
Here?
No, before, I guess. Yeah, this one.
Yeah. Actually, this is where you can define yourself, I think. You need to take several aspects into consideration, such as the structural behavior of the beams that formed by these small elements, and also some design aspect. So I think you can define it yourself, but this is several examples that we showed to you. And the first one, is we use for our tutorials. So I don't think this this is just a fixed option. I think it's also up to you, right? Yeah, to agree, right? Yes. Yeah, I think for the tools we provide, this part it will work for the only this part is only deal with the curves. So if you draw another pattern, you can use this, and this part is try to draw the geometric of the beams. So you can just change this part yourself if you want to define your own.
Yeah.
And then next is collision testing algorithm is based on mathematic line intersection or just the distance calculation. Actually, it's it use it will draw a rectangle in the program. It draw actual geometric rectangle and test if there is any intersection between the rectangle. If they are collide with each other, and then they will be moved away from this part. So it will test if it collides and then move. If there are no collide, this function will just don't be activate. In circle relaxation, after some iterations, the optimization process doesn't help anymore. With more iterations, numbers, the collision won't solve, so we could check and change it manually. I think this problem may occur in a lot of the computational modeling, like the agent-based modeling, because this kind of program or algorithm are trying to solve some difficult problem, like a lot of agents and a lot of behavior they need to deal with. So so finally it will come up with a result, come up a state that try to get a state that is optimum, but I don't think it could solve all the problems in all the situations. So either in the circle relaxation or the program we talked about today, it will all leave some problem that we may need to fix manually by ourselves. To learn more from the online So if you don't have any question, you can try to play with this, and I will update the files, and you can have them later. Anything you want to add, Jakob?
No, I think that's great. I think there was 1 or 2 projects where we said that we would have a look at it later. Could we do that now?
Yes, sure.
Unfortunately, I don't remember which ones that were. Was it Misbah and Mahmoud?
Shall we just go back again and represent the? I think you have already screenshots in our folder.
You want us to send the grasshopper and Rhino file? Is that easier? Or just screen sharing?
Just screen sharing, I guess. Okay. But was it your group where we said that we would want to double check the topos optimization and see what's wrong? Or see how to make it work?
It was not easy actually to play around with the software in my side.
Yeah, I think it was
really helpful to just have a reflection on that, how it works.
I didn't fully understand. I just remember there was one group where the columns.
I think that was Mahmoud and Jennifer probably.
Yeah, okay. Jennifer and Alireza, no?
Sorry, Alireza and Jennifer.
You guys want to check with Hua what might have caused your simulation somehow to ignore the column positions?
Just lost the voice. So shall we just share our screens? Or
yeah, I guess. Yeah, I guess let's just share the screen.
Okay. I guess I saved the mesh somehow. Yeah. I think this that was not the right optimization, topology optimization, what we expected from the software itself. Basically, the beams are kind of intersecting with the model itself. But just now I noticed that one is above and one is, and the other one is under. But I don't think that would cause a problem with the robot surface, or? Which part do you want to see in?
Can you explain where is the problem? Do you have any?
Okay. Yeah, I'm sure. Okay, yeah, so this is, I mean, very kind of coarse lines. I'm not getting the kind of branching that it's supposed to have.
Yeah.
I'm not sure what was wrong exactly.
It's the mesh that you just show. It's the final mesh you get from the optimization.
I'll show you the one.
Yeah, this one.
Yeah.
Is the one you use to generate the length.
Exactly.
But to my view, I think you need to run you need to subdivide it, the structure with more resolution. And maybe run more iterations, you will get better mesh.
So basically, just change the resolution of the
yes,
or
I
the
think
size
so.
of the.
Okay. The mesh don't looks like some very desirable result, and I think what's the cause is maybe the resolution.
Yeah, I used only in this case 30 duration and resolution of 90. I was trying to go as minimum as possible.
You can try.
To increase the resolution.
It will be slower, but it may help.
Okay. One more question: if the load or the youngest model was
I can't hear you clearly.
If the load would affect also the mesh itself or the result, because I was playing around with the load.
Sorry, actually, I can't get you.
Okay. I just changed the load.
Yeah, you can also try to change the load actually, but I think the resolution will have more.
Oh, okay. Okay, so I'll do this. Okay, thanks. I'll just try to play around with the setting. Yeah, I think also there was a thing with the Unix models. I was trying to have a stiffer differently. So I just increase the youngest models. So maybe that.
Actually, I'm not expertise in the
okay,
material aspect. And, what I get from the material is also searching from the website, try to see what's the young model of timber.
Okay, cool. Okay, thanks. I'll just stare on the domain. Okay. Thanks, Phil.
Thank you.
Okay, Alireza. You're muted. We can't hear you. But we see your screen.
Oh, can you hear me right now?
Yeah.
Yes. I just deleted the values and revalued the components here, and the result and the conclusion is different from the first result. And I am really confused, and I don't know what is the reason. Dear Shai recommended that it would be because of the units. I changed the unit to millimeters again and to meters, but I really don't know. It is because of my system or because of not having enough GPU or CUDA. I really don't know. But I would be really thankful if
could you change this to GPU mode and see what
I cannot just change it to GPU mode because my
I mean in the model battery.
Yes, I cannot. It is not enabled for me because my graphic card is GTX 610X, and it is not compatible with Topos.
Okay. But
as you said, and as I read in the texts, it would not have this effect on the results, and
yes, I think so.
we should get the acceptable result. But I really don't know why we have this weird optimization process.
But you didn't run simulation yet, right?
What? I didn't understand.
But you haven't run the simulation right yet.
Okay, I want just
It will take some time.
yes, exactly. I'm afraid of.
Maybe you can don't click. You can change the resolution to a smaller.
Okay.
Maybe like
for example, we can turn it into
30,
20 or
yes.
30.
Maybe
And the number of iterations, okay, it is on 40.
And try it. If it could be faster, just and get it soon.
I guess it would be.
It doesn't work.
No. Yeah, just last night I tried to enable it and I was successful, but here. Okay.
No, this
okay,
not,
I guess
right.
it is because of my system with these circumstances and symptoms we have.
Do you get any error before the optimization in the modeling?
What?
Yeah, no. Sorry. Yeah, maybe I will check your files later and.
Yeah, actually, that thing happened to me also, and it just like reboot things. Like you basically need to close all the things and reopen them, and just try to set the blame multiple times. Hopefully, you'll be able to do that.
I really don't know where is the problem. I checked all the parameters, but you know it is internalized from the previous file. But in my files, for example, in this file, we hope. Oh, oh,
it works.
I think I should restart my laptop right now.
Yeah, but quite slow. Should we wait? I will try to update the files in the Google Drive folder.
I have uploaded the updated file, and I don't know that my teammate, dear Jennifer Rose, have enough just specifications of his system to get a run of. Okay, it's right 15. We can just change, and if some other participants have some questions, and get back on my file. I am ashamed that some just time of other participants are good and they're waiting.
Good. And I have already updated the GH file for today's tutorials. You can get it in the same folder of you.
Just the iteration levels are getting completed. I don't know. Get the results. Oh, my laptop is bursting. and 35. What was the iteration number? It is 48.
Whoops.
Please. Do a little lift. Oh, it is 80. Okay. If these are participants and friends have questions, they can ask until it be completed.
I have a problem with the visualization part of the grasshopper definition.
Yeah.
Since yesterday, I don't know if can you help me with that? Maybe I'll share my screen.
Yes.
I ran the simulation and everything, but like when I display it, nothing shows up. So I ran the optimization, and I increase the resolution as well. But then just this bit here doesn't work properly. I don't know what the problem is.
So nothing. You get nothing here.
Sorry.
You get nothing here in the preview.
No, nothing in the preview. I only get like the point selected, but like nothing in the blurry cloud.
Yes. Can you turn this to the mode to where you internalize them.
These points?
And yeah, see if there are some numbers inside of the.
Should I just put a panel and check if there are numbers?
Yes, can you check what you get? I think the font is fine and numbers. And I think it's also fun. Good. But I don't. Why is this? Can you turn off? I think everything is okay. Can you turn off all the preview of other batteries and just?
Okay. When I turn on everything in the visualization, the whole group, then I get a weird generation. It's like the one you had in the definition you just fixed, like everything overlaps. I kind of get the same thing.
And could you turn? I don't see any. maybe I need to check your files on my computer.
Okay. Because even yesterday when you were running the tutorial, I had the same problem. Only this part wouldn't work.
This part?
Yes.
Would you just go a little bit to the left? Not to the other side, to the other left.
Right?
Yeah, I'm not sure. The other, yeah, this way again, more, this more.
Mm-hmm.
I think those icons here. Try to turn them off on the left, just below the graph.
I'm sorry, I can't hear you properly.
Just below the graph, there's a group, white group. Yeah, there's C preview of the mesh. Just below them, there's the ISO pre-stress icon. I can draw this, right?
This one.
Yeah, those group. I mean, just try to turn them on and see if they show up on something.
Yes, one better did the same thing as the preview we did. Can you go back?
Okay.
Just preview them, make them also to preview. And
this one as well?
No, those, I just turn them on, turn preview on for those icons.
This one. This.
Okay.
Yeah. And this one did the same thing as the one there.
Okay. I'll just use this one then.
Yeah.
Thank you so much. Thank you.
Chris.
I do have a few smaller issues where you might have an answer on. Can I share them with you?
Yes.
You can see my screen?
Yeah.
I was wondering about during simulation, I sometimes see that compliance graph first dropping and then starting to rise again. And I was really wondering what I should think about that and what it means. As in, do you have any background on that or experience with it? Or is it also for you out of your field of expertise?
Actually, I can answer this one, and I'm also this is also confused me a little bit, and maybe we can leave this question to Simon in our expert lecture later.
Yeah, maybe he knows. Yeah, I think the same then holds. I can send you this by email.
Ben, do you have? Yeah, that would be great.
I can send you the one by email, so that maybe you can forward it, then he knows. Good.
Um,
I think the same then holds for the topos boundary condition question.
yeah, if you can horizontally fix it. That
yes.
I wanted to ask you that. Or actually, Chahua, do you know that?
Sorry, I didn't read the question yet.
And,
if you the fixation which is applied through topos, it seems to me that it's going to fixate in z direction, in y direction, and x direction, basically in all the directions. While I would like to fixate it only in the x direction, because it would allow to continue the structure instead of having to module to model a complete separate additional model.
But I don't think topos could provide this function. But it's actually many. It should be an option, and if you use other simulation software like Columbus or Millipede, I think you are able to set the support if whether to fix how many freedom you want to fix XYZ, and also the rotation at 3 direction XYZ. And but here in this plugin, I don't see where we could set this.
Is it an open source project or is complete closed source? Do you know that?
Sorry?
Of Topos is like open source code, or I will Google it a bit and see. If I find a solution, I'll let you guys know. The other alternative would I would suggest is then kind of model a separate structure next to it. I saw in Topos that you can define some structural parts which are always there, which will not be part of the optimization. And I think in that way you can kind of steer your new beams towards these connection points. That may be a way to extend your structure without having to add a complete module.
Yeah.
Good. That's that one. And the last one is when I try to generate those lines, it's gives a mess, and I would expect this one to happen. And I think that has to do with that some areas are enclosed into other areas.
Yes.
We are gonna. I'm able to solve this one manually, so for the workshop it works. But it might be some suggestions to for future improvement.
Oh, okay, thank you. I think that's why we set a slider there for the intersection plan of the mesh, the intersection. Where the intersection happens will decide where the outline of the curves. And sometimes the mesh output from the topos is not that good. And sometimes if you try to bake the mesh into your random model, it will give some warning that this is not a normal correct mesh. And
definitely the case.
Yes. That's why I think that's also why this stuff happens. Sometimes you really need to fix it manually.
Good. Then I have no further questions, and I will share the first one with you by email.
Great.
Okay, great.
Thanks.
And just provide a way to spy on the source code.
All dear friends, do you have my account right now?
Oh, great.
And also my screen. Yes, we had the little victories here, and just it gave us just I don't know if I have baked it or not. Just for the upper. I have this bake invalid object. Wait, this error, as you said. Okay. We have this form of weird boundary, but I think it is because the area of my boundary is not so wide and so big. Just 5 elements, 5 vertical elements. So the meshes would be like this. But I just get a little hope to continue the analysis in other sessions.
Great.
Thank you very much for just hearing me and solving the problem.
Okay. Oh, it's already, we already run over time.
Yeah, so just a quick reminder, please upload your files from today in the day 3 folder. I think we're missing group 6 and 9. And with that, before we close today, I guess the exercise for tomorrow is to continue with your investigations, as you already the ones that you already showed today. For some groups, I think there is a specific need to start working on one project for real together, kind of merging your ideas. Maybe you can identify what kind of responsibilities each of you want to take over during the next days, right? What you want to focus on in your work, and for tomorrow, the greater aspiration would be for you guys to further develop your spatial exploration, but at the same time also try to offer more detail in terms of how you would want to materialize the structure. You can use the tools that we provided you. There is not necessarily a wrong and a right way, right? So whether you use the tools from today with the pattern, whether you want to change that pattern and go into the coding of it and adapt it for your own needs, or whether you want to use the, let's say, more simple approach that we started off with on Saturday. That's all right with us. But the greater idea would be to start showing the beam elements, the wooden elements in your structure, so that we have a bit of a deeper understanding of what that means, maybe structurally, but also most importantly in terms of the visual experience and the logic of it. And then tomorrow we have again a bigger focus on the robotic fabrication. So ideally after tomorrow, like tomorrow morning, you have your beams somehow set, and then you can already start simulating your fabrication sequences during the workshop tomorrow, and then after that for the next day. Yeah, great. I just saw that there is another question online from Sadra. After analysis by topos, the result curves don't intersect with the position of the columns, which define as supports. Is it okay? If you change the column position, the structural behavior is different. Shall we set a new support for the result curve? So I think that's probably not really okay in terms of a meaningful arrangement of beams, right? So, I guess the beams should somehow meet at the column. So that might be a similar problem as we saw with Alireza today, where maybe the meshes are not intersecting during the simulation, and the simulation doesn't understand that the columns are actually support. Sadra, if you upload your codes, then maybe Chahua and I can have
Actually, the mesh generates from topos. It is quite weird that we will always get a void where the columns intersect with the roof, and so when we generate the curves, the network we called, there won't be any curves that are connected to the columns. That I think that's is a problem. But I think in our case, if we have columns directly connected with our slab on top, and we use the beam to reinforce the slab, and so the beam and the column do not have any. It's okay for the column and the beams do not have any connection. So we have our desired result that the beams have already, the beam layout have already reinforced the price.
good. If there is no further questions, then I would say we see each other tomorrow. Have a nice time. Hope all of you are able to properly meet somehow smoothly across continents and across time zones. And yeah, see you all tomorrow. Ciao.